Schrodinger equation, introduced by Erwin Schrodinger in 1926, describes how the quantum state of a physical system changes over time. This fundamental equation in quantum mechanics incorporates both the kinetic and potential energy of the system. It forms the basis for understanding the behavior of particles at the microscopic level and predicts how wave functions evolve over time. The wave function, denoted by psi, is a fundamental concept in Schrodinger's 1926 paper. It represents the quantum state of a particle and varies over time and position. The wave function provides the probability amplitude for finding a particle in a particular state, forming the basis for the probabilistic nature of quantum mechanics. Schrodinger's 1926 paper shows how a particle in a potential well has discrete energy levels. These levels are represented by wave functions, which indicate the probability distributions of the particle's position. This quantization of energy levels is a key concept in quantum mechanics, indicating that particles can only occupy specific energy states. Schrodinger's 1926 paper relates the square of the wave function's amplitude to the probability density of finding a particle. This interpretation, influenced by Max Born's work, shows the likelihood of a particle's presence at a given position. It is fundamental in predicting quantum behavior and visualizing where a particle is most likely to be found in space. In Schrodinger's 1926 paper, eigenfunctions are solutions to the Schrodinger equation that correspond to specific quantized energy levels, known as eigenvalues. Each eigenfunction represents a possible state of the particle, and the eigenvalue represents the energy of that state. These solutions are crucial for understanding quantum systems and the discrete nature of energy levels.